Hello, welcome to another lesson. In this lesson, we are going to be learning hash generation and verification using Python. We'll use the hashlib module, generate MD5 and SHA256 hashes, verify file integrity, and create a complete hashing script. Hash functions are fundamental to cybersecurity for password storage, file integrity checking, and digital signatures. Let's dive in. But before we start, ensure that you have your Visual Studio Code open, just as mine. Once you have that open, you can start writing the code. But before we write code, let me explain what we are building. We are creating a tool that generates cryptographic hashes of files and text. This tool will also verify file integrity by comparing hashes and demonstrates different hashing algorithms. Hashes are one-way functions. You can turn data into a hash, but you can't reverse a hash back to the original data. This makes them perfect for verifying data hasn't changed. This is how password storage works. Systems store password hashes, not passwords. So when you log in, they hash what you type and compare it to the stored hash. Now let me show you what the finished tool looks like. Then after that, I'll walk you through how it works section by section. Now to write the code, the first thing I want to do is to create a file. And to do that, I'm going to type touch, then hash underscore tool.py. And if you look here, you can see my file. So I'll open the file and I'll add the code. And here is the code. If you scroll up, you're going to see that it's a bit lengthy, but not that lengthy. So to test the tool, we can save this, then come to the terminal and run python hash tool.py. At the top, you can see a banner here. And if you scroll down, you can see the list of our options. The first one is that we can hash a text. The second one, we can hash a file. The third one, we can verify file integrity. That is, we can compare two files. The fourth one is that we can demonstrate hash properties. And the fifth one, we can exit. Now, let's start with the first one. We want to hash a text, so we're going to select one. And after that, I can type Victor, then hit enter, and it's going to hash Victor for me. So we are using MD5, SHA1, SHA256, and SHA512. And if you look at it, you will see that MD5 is shorter than SHA1, and SHA1 is shorter than SHA256, and SHA256 is shorter than SHA512. Also, if we select the second one, which is hash file, it's going to ask us to enter the file path. And to do that, you can just copy any file path. Here, I can copy a file path here. Let's say for this log monitoring tool, I can come here and then click on copy path and paste the path here. In your own case, you can create a file in the same directory with your hash2.py and you can copy the path. And even if it is not in the same directory, just ensure that you get the right path and you paste it. After that, hit enter and it's going to hash your file. You can see the hashes here. The next option is that we can verify file integrity. That is, we can compare two files. And to do that, we can create two files. Say I want to create another file here and I'm naming this text1.txt. I'll create another one and name that text2.txt. Now, this is text1, this is text2. So inside text1, I would write Victor is a great man and I'll save. Then here I'll write Victor is a great man too. So I'll save these two. Then I can come here and select 3 to verify file integrity. Now it's asking that I enter the first file path. And to do that, I will come here, right click on this, then copy path, paste the path here. It's asking for the file path to the second file. I'll come here, click on the second file, then copy path to that as well. Then I'll come here and I'll paste that too. Now, if you come here, you can see that it's saying that integrity check failed. Files have different content. So if you look here, we are having Victor is great man. And if you look here, we're having Victor is a great man. So the A that is not there is what is making the integrity check to fail. So if I should come back here and I added A, then I save this and I select 3 again. And after that, I enter the file path to the first file. Then I paste it here. And then I want to enter the file path to the second file. And I paste it here again. Now let me check. Integrity verified files have the same content. This means that even if it is just a full stop that is in one file that is not in another file, the check will fail. because they are not having the same content. So this is how to check file integrity, to know if a file has been tampered with or if the content of the file has been changed or not. Now let's select the fourth option, which is demonstrate hash properties. So we can select 4 and hit enter, and here is going to show you the hash properties. We have deterministic, which means that same input produces same output. That is hashing for you. In fact, if you type Victor 1,000,000 times, in as much you are using the same hash algorithm, it is going to be providing the same hash value to you. So if you look at it, you are having hello world, and if you hash it the first time and you hash it the second time, the hash values are the same. The second property is the avalanche effect, and this means that small change produces different hash. So if you check the text one here, we're having hello world exclamation mark, and the second one we're having hello world then question mark. And because of that question mark, you can see that the entire hash value for the two changes, and that is what we call the avalanche effect. Also, we have fixed size, and this means that output size is independent of input size. If you check here, you can see short input, which is having 2 characters, might produce this, and long input having 520 characters would as well still produce this, which means that both hashes produce the same length, which is 64 characters. And the third one here is fixed size, that is output size is independent of the input size. Regardless of the input size, the output size is always the same. And here is an example. This means that if we have 2 characters here, it is going to produce 64 characters as the hash value. And if we are having 520 characters as an input as well, it is going to still provide 64 characters as the hash value. So this means that the output size is independent of the input size. And those are the hash properties. The next option here is 5. So we can select 5 and we are going to exit the tool. That is how the tool works. Now that we know how it works, let's try to write our code from scratch. So what I'll do is I'll come to the hashtool.py here, highlight everything, then delete it. And we are going to start from the beginning. The first section we need to create is the import and setup section. And why do we need this section? We need it because every tool needs its foundation. Before we can hash anything, we need to import Python's cryptographic library and utilities for file operations and program control. This section sets up all the tools we are going to use throughout the script. You can think of this as gathering all your tools before starting a construction project. And this is what the section looks like. Now let's understand what it does. Here we are importing the hashlib, which is a Python's built-in cryptographic hashing library, and it provides MD5, SHA1, SHA256, SHA512 and other algorithms. We also import sys for clean program exit functionality when users quit or when errors occur. And we are importing OS as well for file operations like checking if files exist and getting file sizes. The beautiful thing about hashlib is that it is part of Python's standard library. No installation needed because it is always available on any Python installation, which makes our tool portable. Now let's move to the second section, which is where we are going to write the hash text function. And why do we need this function? We need it because it is our core text hashing function. Since we are going to be hashing, so users need to hash passwords, passphrases, or any text data to see what the hash looks like. So this function takes plain text and converts it to a cryptographic hash using any algorithm we specify. It is the foundation for all text-based hashing operations in our tool. So this is what the code looks like. So if you scroll up, you will see the beginning of the function. This is the beginning and this is the end of it if you scroll down. Now let me break this down. First, in this function, we are converting text to bytes using encode with UTF-8 encoding. And this is critical because hash functions work on bytes, not strings. So UTF-8 encoding converts the string to its byte representation while handling all Unicode characters properly, including emojis and special characters. After that, we are creating a hash object based on which algorithm the user selected, and each algorithm has its own function. We have MD5, SHA1, SHA256, or SHA512. So after that, we are passing the data directly to the hash function, which creates a hash object that has already computed the hash internally. Finally, we call the hexdigest to get the hash as a hexadecimal string, because this is the standard readable representation you see everywhere, just something like what you can see on my screen right now. And why are we using hexdigest instead of digest? The digest method returns raw bytes, which aren't human readable or easily comparable. So hexdigest converts those bytes to a hexadecimal string that we can read, display, compare, and store in text files. Now let's move to the third section, which is the hash file function. And why do we need this function? We need it because text hashing is useful. But real security work involves hashing entire files. Downloaded software needs verification. System files need integrity checking. Also, disk images need forensic hashing, and this function handles files of any size efficiently by reading them in chunks so that we can hash gigabytes files without running out of memory. This is what makes our tool practical for real-world use. And this is what the code looks like. It starts from here. You can see the hash file function here, and then it ends here. So let me provide an explanation to this function. In this function, first we create an empty hash object. And also you should notice that we don't bypass data to hash function initially like we did with text, because here we are feeding data to it incrementally as we read the file. And after that, we open the file in binary mode with RB. Binary mode is absolutely critical here because we need the exact bytes, not any text interpretation or encoding conversion. A single wrong byte would produce a completely different hash. So we read the file in chunks of 4096 bytes. And why chunks? Because if you have a 10 gigabyte ISO file or disk image, you can't load it all into memory at once. Your program would crash with an out of memory error. So reading 4 kilobyte chunks, that is 4096 bytes, keeps memory usage constant and low regardless of file size. You could hash a terabyte file and never use more than a few megabytes of RAM. Also, for each chunk, we call updates on the hash object. And this adds the chunks data to the running hash calculation. The update method can be called multiple times and it correctly accumulates the hash across all chunks. The final hash is the same as if you had loaded the entire file at once. So when read returns an empty byte object, that means we've reached the end of the file, so we break the loop. Finally, we are returning the hexdigest just like the text hashing. The try except blocks handle common errors gracefully. Errors such as file not found, permission denied, and any other file reading errors are caught and reported with helpful messages. This makes our tool robust and user-friendly instead of crashing the cryptic Python tracebacks. Now to the next section, which is where we are going to hash text with all algorithms. And why do we need this function? We need it because users shouldn't have to call hash text function 4 separate times to see how different algorithms work. This convenience function hashes the same text with MD5, SHA1, SHA256, and SHA512, and it does this all at once. It also displays the results side by side for each comparison, just as we saw it when I was doing the demo earlier. It is perfect for educational purposes because it shows us how different algorithms produce different hash lengths and values from the same input. Now, this is what the code looks like. You can see that from here down here. So let me explain how this works. We start this function by printing a nice header showing what text we are hashing, and if the text is longer than 50 characters, we truncate it with ellipses to keep the display clean and readable. We also create a list of 4 algorithm names and loop through them. For each algorithm, we call our hash text function with that algorithm name and immediately print the results. The f-string formatting you are seeing there is clever. For example, if you look at this, you can see the algo.upper and you can see 8 in front of that method. This means that we are converting the algorithm name to uppercase and then we are padding it to 8 characters wide. So this creates perfectly aligned output that is easy to read. This alignment makes it immediately obvious that different algorithms produce different hash lengths. MD5 is 32 characters, SHA1 is 40, SHA256 is 64, and SHA512 is 128. Now that we are done with that, we can move to the section where we hash file with all algorithms. The previous one we did was for text, so this one is for file. And why do we need this? Just like that of text, users want to see how different algorithms hash the same file. This function hashes a file with all 4 algorithms and displays the results together. It also shows file size information, which helps users understand that the hash length doesn't depend on the file size. A tiny 1 kilobyte file and a massive 10 gigabyte file produce the same length hash for a given algorithm. Now let's see what the code looks like. So here is the code from here down here. So if you look at this function, you are going to see that first we verify the file exists using the os.exist method, and this prevents cryptic errors later if the file doesn't exist. So we fail fast with a clear error message instead of running into trouble. After that, we get the file size with the os.path.getSize method and display it in both bytes and kilobytes. This gives context about what we are hashing. The format here divides by 1024 to convert bytes to kilobytes and formats to 2 decimal places. After then, we loop through algorithms like the text version. So for each algorithm, we call hash file and print the result. We then check if hash value is not none before printing in case there was an error during hashing, like permission denied or file became inaccessible. This function demonstrates an important hash properties, which is fixed output size. So whether you hash a file of 1 byte size or a file of 1 gigabyte size, SHA-256 produces exactly the same 64 hexadecimal characters. Now let's proceed to create the file integrity function. And to create that, this is what the code looks like. It starts from here and you can see it. So what does this code do, or how does it work? This function compares 2 files by comparing their hashes, which is brilliant for several reasons. First, if you look at the code, you can see that we are verifying both files exist, because there is no point trying to hash files that don't exist. So we decided to fail early with clear messages if the file does not exist. After that, we then compute SHA-256 hashes for both files, and we are using SHA-256 specifically because it is secure, widely used for integrity checking, and fast enough for practical use. After that, we then compute SHA-256 hashes for both files, and we are using SHA-256 specifically because it is secure, widely used for integrity checking, and fast enough for practical use. After that, we are now checking if either hash is none, which could indicate an error reading the files like permission denied or input-output error. We then display both hashes so that users can see them. This is important for transparency and record keeping. And finally, we simply compare the hash strings with the equality operator. So if they match, the files are identical down to the last bit. If they don't match, the files are different somewhere. This is much faster than comparing files byte by byte. A 1 gigabyte file produces a 64 character hash, and comparing 64 characters is instant. Comparing a billion bytes would take significant time. So our hash comparison scales beautifully. The next section we want to write is the demonstrating hash properties function, and we saw that earlier when I was running the demo. So we'll step down and we write our function here, and you can see the function from here down to here. So let me quickly walk you through each property demonstration. The first one here is the deterministic property, or we call it determinism. If you look at it, you can see that we hash hello world twice with hash256. And both hashes are identical. So this means that this property is fundamental. That is, given the same input, a hash function must always produce the same output. Without this, hashes would be useless for verification. And the second one is the avalanche effect, and you can see that here. Here we are hashing 2 nearly identical strings, which are hello, world exclamation mark and hello, world question mark. And as you can see, the only difference is that one character changed from exclamation mark to question mark, but the hashes are completely different. In fact, they are sharing no apparent pattern. And this is the avalanche effect. That is, a tiny change in input causes a massive change in output. This property makes it impossible to predict how changing input will affect the hash. The third property is the fixed output size. This means that if we hash a 2-character string which is high and the 500 plus character string, both will produce SHA-256 hashes that are exactly 64 hexadecimal characters. The hash length depends on the algorithm, not the input size. SHA-256 produces 256 bits, which is 64 hexadecimal characters, whether you hash 1 byte or 1 terabyte. It produces the same output length. So these three properties together make cryptographic hashes incredibly useful for integrity checking, password storage, and digital signatures. Now let's proceed to the main function, which encapsulates the menu structure. The main function is our program control center because it creates the user interface. And not that alone, it also handles menu navigation and coordinates all the hashing functions we've built. This is what transforms our collection of functions into an iterative tool that users can actually use. The menu-driven interface makes the tool accessible to both beginners and experienced users. And here is what our code looks like. You can see from where we are defining the function here down to this point. So let's understand the menu structure properly. The main function starts with a professional title banner that clearly identifies what the tool does. And as you can see here, we have hash generation and verification tool, and under it we have cryptographic hashing with Python. So this is the first thing the users see. After that, we then enter an infinite while true loop, and this keeps the program running until the user explicitly chooses to exit. After each operation, the menu reappears, meaning that it is ready for the next task. Also, if you look at the loop, you see that inside the loop, we are displaying the menu with 5 clearly labeled options. Each option has a number, making it easy for users to select what they want. We use input to get the user's choice because input always returns a string. So 1 is a string, not a number. For option 1, which is for text hashing, we are asking the user to enter text. After that, we validate that the text is not empty before processing because empty text would produce a hash, but it's probably a mistake, so we catch it and show an error. If there is text, we call the hash text all algorithms, which we built earlier. This hashes the text with all 4 algorithms and display the results beautifully. This simple validation prevents confusion and improves user experience. Now let's consider the file hashing and comparison options. And to do that, we are going to be using elif. For this section, users need easy access to file hashing and integrity verification. So these menu options connect user inputs directly to our file hashing functions. Option 2 lets users hash any file to see its cryptographic fingerprints, as you can see earlier in the demo. And option 3 lets users verify 2 files are identical without manually comparing hashes. So this is what that would look like, as you can see from elif here down here. So if you look at the first elif, you will see that option 2 asks for a file path and immediately calls the hash file all algorithms. We don't need to validate existence here because hash file all algorithm already does that internally. It will display a clear error if the file doesn't exist. And if you look at the second elif, which is for option 3, this one is asking for 2 file paths and calls verify file integrity. Again, the verify function handles all validation, checking if both files exist before attempting to hash them. You should notice how clean this code is because you can see that each option is essentially one function call. All the complexity validation, error handling, and formatting is encapsulated inside the functions we built earlier. This is good software design because the main function orchestrates and the specialized functions do the work. Users can now hash files, compare downloads to publish hashes, verify that backups haven't corrupted, or check if 2 files with different names are actually identical. Now let's move to the demonstration and exit options. And for that, we are going to be using elif, else, and after that, we are going to write our if name equals main section. So this is what the code for that looks like. You can see from elif choice 4 here down to the if name equals main section here. And let me quickly break this down. Option 4, as you can see here, calls demonstrate hash properties, which builds to show three key properties of hash functions. And this educational feature helps users truly understand what they are doing, not just blindly using the tool. And for option 5, we are printing a polite goodbye message and calls the sys.exit message. And the message we are displaying is exiting hash tool. The zero parameter we have in our sys.exit method indicates successful termination. In Unix and Linux, exit code 0 means everything worked perfectly. Non-zero codes indicate errors. And for the else section, this handles invalid inputs. So if someone types something like 6, 7, or any number that doesn't exist in our option, or probably a string like hello, Victor, or any other thing aside from 1 to 5, we tell them it is invalid and show them the menu again. This program doesn't crash. It just asks them to retry. And that is what the else function here is doing. So for the last section here, the if name equals main block is Python standard entry point pattern. It ensures the code only runs when the script is executed directly, not when imported as a module. So we wrap main in try except to handle unexpected events. The keyboard interrupt here catches Ctrl+C and lets users cancel gracefully without seeing ugly Python traceback. The generic exception catch handles any other unexpected errors, displays them cleanly, and exits with code 1 indicating an error occurred. This makes the tool professional and user-friendly from start to finish. And now that we are done building the tool, we can save our code and come here to run the code again. So we hit enter and you can see that we are seeing our option 1 to 5 again. So you can select option 1, type anything, Victor is good. And as you can see, it has provided the hash value. So if you run it for the remaining options, that is option 2 for hashing file, 3 for verifying file integrity, 4 for demonstrating hash properties, and the fifth one to exit, you are still going to get the same result as what we got when we're doing the demo at the beginning of this lesson. So that's all for this lesson. But before we go, here is a challenge question for you. And the question is, what is the difference between MD5, SHA1, SHA256, and SHA512? I repeat, what's the difference between MD5, SHA1, SHA256, and SHA512? I'll be waiting in the comment section to get your responses. Thank you so much for seeing the video till the end. If you're yet to subscribe to our YouTube channel, please do that now. Also, do not forget to like, share, and comment. Thank you, and see you in the next lesson.